Hello, everyone, and thank you for attending the Open Environmental Restoration Resource webinar on vapor intrusion, tools, and technologies. My name is Amy Hawkins. I work at NAVFAC Exwick in Port Hueneme, California, and I'm going to be your moderator for today. Part of my duty as moderator is to provide you with the information you will need to successfully navigate today's webinar. Next slide, please. All participants are connected in a listen-only mode. If you have any questions, use the Ask a Question button on the lower right-hand side of your screen, and your question will be sent privately to the host. Questions will be answered at the end of the presentation during the question and answer session, but please enter your questions throughout the presentation as you think of them. As an attendee, you have the ability to pause the webinar playback. If you need to step away or while you type a question, you can find a pause play button in the lower left quadrant of your screen when you hover your mouse. This presentation is being recorded and an archive of the presentation will be available on the ERB website. Following the webinar, a link will be available to a short survey. Please fill out the survey as it is our main feedback mechanism and should take less than 2 minutes to complete. I would like to emphasize the following important disclaimer. This seminar is intended to be informational and does not indicate endorsement of a particular product or technology by the Department of Defense or NAVFAC Exwick. Although every attempt is made to provide the most accurate information, there is no guarantee that any technology or product will be suitable for your site. And as always, participation on the webinar is voluntary. Next slide, please. Our speaker today is Travis Lewis. Travis works at NAVFAC Exwick out of Port Hueneme, California, where he is involved with technology transfer, evaluation, and demonstration of innovative technologies, and in providing specialized technical support to the RPMs. Travis earned his MS as a civil and environmental engineer from the Colorado School of Mines. His experience includes several research projects directly related to today's topic. Before Travis begins the presentation, I would like to invite Gennady Coughlin from NAVFAC headquarters to say a few words about the OER2 webinars.
Thank you, Amy. Hello, everyone. Good afternoon. Good morning. I am Gennady Coughlin with NAVFAC headquarters. Thank you for participating in the Open Environmental Restoration Resources, or OER2 webinar series. We know how busy everyone is, and we appreciate the time dedication to this webinar. Since its launch in 2014, the OER2 webinar series has become one premier outreach tool across our ERP community. The participation, enthusiasm, and feedback received from the AR community so far remain high. This webinar series is for RPMs, RTMs, contractors, and others who support Department of the Navy Environmental Restoration Program, or ERP. Our goal is that the series will provide a two-way communication forum for reaching out to and obtaining feedback from the community members. The emphasis of the webinar series are open sharing information and promoting innovation among the community members. This can be in the form of policies, guides, tools, technology, best practices, initiatives, or lesson learned. As I mentioned, feedback from the community members is key to sustain this series. I would like to also remind our community to actively recommend topics or volunteer as presenters. Case studies highlighting lesson learned, innovation, and strategy toward response complete goals, for example, are highly relevant. If selected, a NAVFAC champion will work with the presenters. For contractors, please reach out to the RPMs and start looking at your Navy site portfolio. Today's webinars on vapor intrusion tools and technology is very important topic for the ERP. There is a large disparity between EPA and OSHA standards that continue to be ongoing challenges for RPMs when determining how to address indoor air on several Navy sites. The Navy continue to address the issue of rapid response at VI sites on a site-specific basis. Department of Defense, through the Tri-Surface Environmental Risk Assessment Work Group, has developed several fact sheets as appendices to the DoD Vapor Intrusion Handbook to address the specific issues. Technology described in the fact sheet will be discussed on today's webinars, along with the pros and the cons of the associated with these technology. So with that, let's hear from our presenters, Travis Lewis. Travis.
Hi. All right. Well, thank you, Amy and Gennady, for the opener. During the duration of these slides, we'll be talking about tools available to investigate this invisible world of vapor intrusion, which I'll be referring to as VI. Herein, as you see enlisted here, is a roadmap of today's discussion, which will hit on some of the latest advancements in this world of VI. So let's dive right in. Before we dive into all these technologies that was listed before, I think it's important to provide a brief overview of VI. Presented here is a typical conceptual model of an industrial VI site where you'll have offices situated within a larger industrial warehouse with, as you can see up above, a air handling system that delivers heating and cooling to this warehouse. Within the subsurface, you'd have either shallow or ground or a deep aquifer that may be contaminated with VOCs. In this example, say we have high levels of TCE in the groundwater that is volatilizing TCE into the vapor phase as soil gas, which has migrated upwards through this vapor zone to reside beneath the building envelope. Herein, concentrated soil gas may migrate into this building envelope via cracks in the foundation, or say through sewer utilities and conduits, as you see here with floor drains in the bathroom and break room. And this can lead to possible VI exposure. Now, within the Navy's portfolio of large industrial buildings, many of these structures were built during the World War I and World War II wartime efforts, which were not really designed for heavy usage over multiple decades. Consequently, several of these warehouses exhibit signs of structural wear that can facilitate subsurface migration of vapors through fractures in the foundation. As you can see in this picture, with cracks along the wall, this was taken from one of our industrial sites, which we'll be actually discussing as our case study for a number of the example technologies. So this phenomenon of vapor migration through fractures or via floor drains is a more pronounced during periods of heating, which you'll observe in the winter season, whereby HVAC systems pull in air, creating negative pressure in the building envelope, which can act as a vacuum, pulling these vapors through the subsurface. And we'll be discussing examples of this scenario that have been observed in a few of our case study examples. So speaking of case study examples, this is an appropriate point for us to just dive right into this VI world of technologies. So in this invisible world of VI, there are emerging methods to address every challenge that allows us to more or less peer under this cloak of invisibility, say, to see these elusive gases. And here are the more common technologies you see listed. Although there seems to be a lot of opinions and a lot of options available for investigation of VI, the key is to be aware of them, know their purpose, and how to communicate their value effectively to regulators and stakeholders. As shown in this slide, I've created some general baskets that these different technologies can fall into, but we'll be discussing these topics highlighted in greater detail. We'll not be discussing tools for assessing background contribution, as these methods have been around and in practice for a long time. But for your viewing pleasure, you need something to read at night, we offer in-depth review of each of these technologies via, as Gennady mentioned, fact sheets. And one specific fact sheet I would call your attention to is the Navy's VI Matrix of Technologies fact sheets, which can be found publicly on the DNEX website. The link to this site can be found at the end of this presentation, where I show you all the resource material. So let's dive right in. First stop on this VI train will be continuous real-time monitoring tools. Namely, I'll discuss GC-ECD, or gas chromatography and electron capture detector unit. Try saying that 10 times over. But to avoid that tongue twister, I'm just going to refer to it as the GC-ECD unit. So seen here in the graphic on the right, the GC-ECD is a large portable instrument which supports real-time decisions and enables a cause and effect refinement of your CSM, or conceptual site model, and identification of indoor vapor sources. Unlike a PID, the GC-ECD is able to provide compound-specific concentrations as opposed to a PID, which would give you only total VOCs. The GC-ECD can extract specific compounds such as TCE, and unlike the HAP site, which also provides compound-specific concentrations, the GC-ECD can analyze several compounds simultaneously from various building units using multiple sample ports. Generally, you'll find 20 sampling ports on a GC-ECD unit, though some have as many as 50 or more. Being able to rapidly interpret sources can lead to significant cost savings related to site sampling. Now for the caveat. The word simultaneously should really come with quotation marks around it. Although you can draw in air samples from multiple sampling units at the same time, so sampling zones, say bathrooms, offices, the GC-ECD can only analyze these samples one at a time. And the runtime for each compound is about 10 minutes. So say you're using all 50 sampling ports and you have tubing running to 50 different building units. So you have one going to a restroom, an office, a break room. You won't be able to analyze all 50 sampling ports for TCE in 10 minutes. It'll be roughly 8.5 to 9 hours to complete this first round of sampling. So in a given day, you'd only be able to collect 2 to 3 sampling cycles from all the different building units per day if you're using all the sampling ports simultaneously. Another limitation to consider is cost. These sampling units run about $200,000 to purchase, plus labor and material costs for tubing installation. And you're trying to sample both. And if you're trying to sample both indoor air and subslab soil gas concentrations simultaneously, you'll likely need 2 of these units due to sensitivity requirements to measure, say, single-digit ppb concentration for indoor air versus the 100,000 plus ppb you may see in the subsurface for, say, TCE. And this can cause breakthrough challenges and calibration issues with these instruments. So given the fact that these units require a dedicated, given that these units require a dedicated space to run undisturbed, there may also be challenges in identifying a suitable space to situate these units given their size and need to be operating undisturbed. So, but as we mentioned before with the fact sheets, if you're looking for greater information, we offer a fact sheet on the real-time monitoring for vapor intrusion assessment via the DNEX website. A little icon or image you see in the upper right, that's a screenshot of the fact sheet. And this also provides information on HAP site, PID, and other real-time instruments. So diving right into an example, in a more recent study completed this past January using NESDI Naval Research Funding at Norfolk, we deployed a GC-ECD for 1 year collecting vapor samples from 7 subslab locations, which are shown in In yellow, you have to look for the ones that say ESV, and which were co-located with 10 indoor air locations. So all the yellow icons you see were taken with the GC ECD, and the orange was Radon, which we'll discuss in this lecture, which would represent an excellent surrogate for VOCs, as it's not commonly found in indoor air products and can indicate vapor intrusion. And then we took some differential air pressure as a indicator, which I'll be discussing indicators and surrogates and tracers in greater detail, but where you see in orange is where we were trying to get indoor air pressure changes. So now when we look at the 1-year data collected from the GC ECD over the course of a year, we see some interesting observations. First, I'll call your attention to what you're seeing here. In the top figure on the x-axis are dates, and the y-axis is TCE concentrations at log scale. The colored dots represent different building units. The yellow and orange dots were from the building zone 2, which was the break room and restroom, which if I go back, the break room and restroom was the bottom purple zones. So that was the kind of the middle bottom purple. And so when we were looking at these the break room, we saw some interesting peak rises, which were the orange and yellow dots, which intersected with had the sewer utilities intersected with contaminated shallow groundwater, which was contaminated with TCE. And the sewer utilities allowed vapors to migrate into the building. Another interesting point is when we see these spikes in concentration. So from May through September, these concentrations are largely stable and below the 1 ppb in that top graph that you see. However, in the winter months, say October through March, we see a lot of peaks above the 1 ppb and at times above 10 ppb. And this was due to the stack effect that is observed during the heating or the winter season, where, as we mentioned earlier, when you heat up a building, the air handling system will suck in air, which create a negative pressure differential or a vacuum, and can pull vapors in from these leaks in the subslab, and in this case, the floor drains. And when you look at the subsurface, which is the bottom figure, which again has dates on the x-axis and log scale concentrations for TCE and the y-axis, we see very little variability over time. Each of the colors represents a different sampling location, and although the concentrations at each sampling zone differ, the variability at each sampling zone varies relatively little over time. This demonstrates that seasonal variability had little influence on concentrations in the subsurface, but can have significant influences on indoor concentration due to the operation of the HVAC or air handling system. So I mentioned tracers and surrogates a few times in the previous slide. This is an appropriate point for us to just explain what these means and how they can help you identify possible vapor intrusion exposure. So it isn't always necessary to measure VOC's concentration directly to figure out whether vapor intrusion is occurring. And sometimes the data is just too complex by background sources and variability. Background sources may be just being spray-on degreasers that you may have in indoor air products, or from outdoor air with traffic contamination migrating into the building. So tracers, surrogates, and indicators are alternative measurements that can provide information that is not subject to the same biases and can therefore be very useful. Now for the distinction. So tracers are constituents that can be brought to a site, injected, and assessed. Surrogates are naturally found in the environmental setting, and indicators are, you could say, as a tertiary properties that can be used to indicate possible presence of a VI phenomenon, such as building pressure and temperature. And I'll provide some greater clarity with some text and examples. So starting with tracers, which are usually inert compounds that have very similar properties as the compound of interest, say TCE, that we want to assess via VOC migrations. Now, you may say, well, geez, Travis, if you want to assess TCE migration, why don't you just measure TCE? It's like if you're trying to find a masked robber, just look for a guy with a mask. But if you look outside these days, everyone is wearing a mask. So similarly with TCE, along with a whole suite of other VOCs, they can be found in a laundry list of indoor air products and can contribute to ambient background concentrations. So especially in an industrial setting, as I mentioned, you may find TCE off-gassing on machine parts, used in spray-on degreasers, or outdoor VOCs from vehicles, which can confound your assessment of VI exposure. So you don't want to be saying there's a VI risk when in fact it's due to normal building operations and thereby creating a false positive scare. So to remedy this issue, you may want to consider tracers such as sulfur hexafluoride or SF6, which is a man-made non-toxic inert gas, or helium, which is not commonly found in indoor air unless you say you work in a circus, but both of these can be injected as a tracer beneath the building subslab and measured in the indoor air to assess slab leakiness. However, especially in a large industrial warehouse where the footprint can be upwards to 1 million square feet or more, it can be challenging to ensure adequate coverage of injected tracers and ensure you're injecting enough to have it be measurable concentrations. So you'll need to consider dilution as you do this injection. To address this challenge with tracer, as I mentioned, with especially with a large footprint, you may want to consider surrogate compounds, which are already found in the subsurface and likely provide ample coverage of the whole building footprint, or at least in the same areas where VOCs are most present. So as I mentioned previously, radon is a great surrogate for VIs. It's naturally occurring and easy to monitor indoor air via radon samplers that can measure radon. However, you need to ensure radon is high enough to be measurable. Some states have naturally low radon in their bedrock, such as Texas and Florida, which can reduce the application of this tool. Secondly, ambient radon from outdoor can be very high, which could give a false positive indication of leakiness of a slab, such as North Dakota and Montana, which have average indoor radon levels above 4 picocuries per liter. Point being, just know in advance whether you live in an area with either naturally low or high radon. This can impact your assessment. Alternatively, as far as surrogates go, you can consider 1,1 DCE or cis 1,2 DCE, which is not commonly found in indoor air products, but is a degradation product of, say, TCE in the subsurface. But again, it needs to be high enough concentrations to be measurable, preferably, say, above 5,000 ppb in the subsurface. When you have indicators, which I wouldn't rely too heavily on by itself, but can be used as an additional line of evidence to support presence, absence determinations, that can be total VOCs from the building foundation and cracks, such as floor drains using a PID, taking infrared temperature profiles of the same features. Generally, subsurface air is cooler than indoor air, so you could possibly see a cool air stream from the foundation in the leaky spots in the say in cracks. So that would give you a distinct temperature profile. And as we mentioned previously, building pressure can cause vapors to migrate into a building if you observe negative pressure gradients, such as in a range of -5 to -15 pascals. So building pressure is another important indicator, and I'm going to be going into examples for these in the next slide. So back to examples with respect to the NESDI 554 case study in Norfolk. This data was taken from the supply room, which was a controlled building zone with minimal traffic, so people weren't coming in and out regularly. The top figure is a surrogate example with radon. And the bottom is an indicator example with differential pressure. So viewing both of them, both have on the x-axis we see time. The top figure, radon is compared to TCE. Radon is in red, TCE is in blue, and one of the y-axis, on the y-axis we have concentration, and on the left is a log scale for TCE, and on the right is radon concentration, not log scale. And what we see here is a positive correlation between radon and TCE. When radon concentrations are lower, we observe lower concentrations of TCE. Likewise, when we observe peaks in radon, we observe associated peaks in TCE, which I have boxed for both of them. This was indicative of a preferential pathway in the subsurface that was facilitating migration of radon and TCE alike through the heating season, which via the air handling unit was pulling in air and creating a negative pressure gradient that facilitated migration of VOCs. So speaking to pressure gradients, we have daily measurements again of TCE, shown in blue, and differential pressure shown with the black line. And looking at the pressure, we see when the building zone was above, say, 0 pascals, which was during the cooling or no operation of HVAC system, TCE concentrations were below 1 ppb. However, during the heating season, in the winter months, when the differential pressure dips below 0 pascals, we observe high TCE concentrations, showing a positive correlation between TCE and building concentrations. So here we're showing you a tracer example using SF6, and these HVAC or sampling zones displayed in the first column were originally identified by conducting a detailed building survey. So once the HVAC zones had been identified, a detailed inspection was conducted by an HVAC specialist, and as part of the tracer testing using SF6, we were able to get baseline air exchange rates that were used to, using a decay method. So shown in the table, I want to explain what these columns are. ACH, that's the air changes per hour. CFM, that's cubic feet per minute. And SF6 is sulfur hexafluoride, which is a non-toxic, non-hazardous, non-flammable gas that is not commonly found in the environment, that acts as an excellent tracer to measure gas movement. So this table shows the calculated air exchange rates for each zone. I've highlighted 2 zones that we'll be discussing in depth. Now, how the several different spaces within zone 2 have, if you notice, they all have pretty similar rates, right around 3 air changes per hour. Also note that the air change rates in zone 4, which is in yellow, the supply rooms is over a magnitude lower than the other ones, than say zone 2. And so a supply room with the data we observed in the previous figure with the radon differential pressure, what this data indicates was the radon is more effective in predicting VI in sampling zone as you observe low exchange rates. As I mentioned previously, you want to ensure that you have measurable radon in the subsurface, but you also want to ensure that you have air exchange rates within a building that is low enough to not dilute the radon and impact your ability to measurement. So here we're using a tracer, which may be useful to get an accurate assessment of your air exchange rate if this information is not readily available by, say, an on-site HVAC specialist. And this information can support your decision to possibly turn off or reduce the air exchange rate so you can properly assess radon or other surrogate constituents as you build your body of evidence to support a VI presence or absence determination. Okay, moving right along. Next up is building pressure cycling, which many of you may already be familiar with. So building pressure cycling is a tool at our disposal for essentially turning VI on or off when a preferential pathway is present. Instead of waiting, say, weeks to a month with GC-ECD, with tubes running through various building units and collecting data over a prolonged period of time, you can get an estimate of near worst case exposure within a matter of a few hours. And as we discussed earlier, building pressure has a significant influence on VI exposure. So if you can bring the building pressure down to the most negative differential pressure that that building would typically experience during normal operation, you can gain immediate insight as to whether you have a possible VI exposure. However, this technology isn't perfect. The biggest challenge is inducing negative pressure, especially if you're dealing with a massive industrial warehouse where there just may be too much volume for the HVAC system to adequately create consistent negative pressure. Or in older buildings, as we have in the Navy's portfolio, there may be several fractures in the walls, ceilings, and windows that can compromise your ability to induce appreciable pressure changes. In this instance, you may be able to induce localized pressure reductions in smaller building units within, say, the warehouse, such as a temporary office or a break room or rest room, using blower doors. And these can be brought to a site, fitted to a standard door, and sealed to push in air or pull air out of the room to induce pressure fluctuations and assess VI exposure using real-time instruments like as a HAP site, which is shown in the graphic on the right, where they installed a blower door into an office and induced pressure fluctuations, used a SUMA canister to collect data for lab analysis, and used a HAP site to get those the real-time changes in TCE concentrations. But here's a bit more detail on turning on and off VI. You can do this by means of manipulating the HVAC system to change interior pressure, or at the blower door, as I mentioned. For instance, when you're pulling in air into an HVAC system, we're depressurizing a building. So that's the figure on the top left, thereby turning VI on. Conversely, if you push air into a building, you're inducing positive pressure conditions, which suppresses vapor migration into the building. And here you're turning off VI. As I mentioned, you can do this with blower doors in an office or a restroom. A critical component of this method is to ensure you're operating within the normal pressure ranges, which is typically +5 to -10 pascals. You don't want to be inducing unrealistic pressures on a building such as -50 pascals, because you would be creating artificial conditions that would never exist. And you'd have a hell of a time opening these doors if you did create such a vacuum, because you would possibly crush your fingers with the amount of pressure induced. So you want to ensure that you're using realistic ranges when turning on VI. You don't want to create a worst case. You want to create a worst case scenario that is realistic to building pressure conditions that you'd see over the course of operation. And you can determine this by either asking your local HVAC engineer, which is recommended, or doing field testing with, say, a manometer connected to a data logger as you measure pressure fluctuations within the building. So on to an example, back to our NESDI 554 study, where we attempted building pressure cycling. Due to the advanced age of the industrial warehouse, we were unsuccessful in generating consistent negative pressure throughout this large warehouse. There had been, what was observed was there had been an earthquake within, say, the past half century that had damaged the walls, which created a significant leak for air to migrate freely. Along with, there were several windows within this industrial building that had broken panels. So as we tried to induce pressure, we weren't able to get any sort of consistent pressure. So what we ended up doing was moving forward with using blower doors within the smaller building units. The data shown here is from the supply room, where you saw the radon data, and the break room. First, with the figure on the left, is from the supply room for TCE. X-axis is the differential pressure, starting from -5, -10, -15, and +5 pascals. Y-axis is average TCE concentrations that was measured with a HAPsite. And we see a negative pressure below, when pressure got below -5, we observed higher TCE concentrations, which indicated a presence of a VI preferential pathway, because we were able to induce higher concentration with greater negative pressure. If there are no leaks in the foundation, then we wouldn't observe any fluctuations in TCE concentrations under both positive or negative pressure conditions. Similarly, with the figure on the right, we observe pressure in the x-axis with different colors representing different VOCs. Similarly, focusing on cis 1,2 DCE, which, as we previously mentioned, is not commonly found in indoor air products. And at more negative pressure, we observe greater concentrations, which is indicative of a VI preferential pathway where cis 1,2 DCE is being pulled from the subsurface. In both instances, we were able to apply building pressure cycling to identify a VI preferential pathway in a relatively short period of time, of a matter of a couple of hours. So, getting on to the last bit of our technology train. Last stop is high volume sampling. This tool is really neat, more or less an all-in-one tool, and with a relatively short period of time, you can assess soil gas concentrations, contaminant distribution, and slab leakiness over a pretty massive area. So general concept follows the cone of depression that you would observe with, let's say, a groundwater well. You'd install shallow pipe penetration through the subslab and have a vacuum pull air. And through a series of pressure monitoring points, you can assess the capture zone for subsurface vapors. Now, I'll show you several slides to make this point more clear. And we also have fact sheets on the DNX site as a reference. So some quick pros and cons before I jump into the case study. For the advantages, the HVS system, high volume sampling, enables fewer sampling locations, helps identify missing hotspot areas, enables soil gas sampling in non-accessible areas, say beneath an active building zone, and enables data for installing a subslab depressurization system. So it supports your data needs, how much volume or flow requirements you may need, and understanding what is the radius of influence for extracting subsurface gas. Now, some of the limitations is it's not usable in low permeability soils such as clays or wet soils, or sites with shallow groundwater right below the subslab. You just can't generate enough airflow in those low permeability areas. You would need to manage the extracted soil gas, but this can be typically mitigated by just running an exhaust line to the outside. There's more equipment needs than, say, conventional subslab sampling, which you'll see, but it just requires a few more components, and it can be more disruptive than conventional subslab sampling. You'll likely need to conduct, say, this investigation over a weekend. But jumping right along to an example. So within the DoD, we have some colossal facilities, and one such is this Black Hawk helicopter maintenance facility in Naval Air Station, Corpus Christi. It's a massive 20-acre building that rests over a large TCE plume, and it's just not feasible nor economical to just Swiss cheese the whole building with pilot holes and 1-liter Suma canisters. You're either going to have way too many samples, or a hefty bill, or a high risk of missing important hotspots between a fewer number of sampling zones. So to top it off, as I mentioned, this is a Black Hawk helicopter maintenance facility that is highly restricted to access and has sections completely closed off to even the most charming consultants. So if you go in there, you may not come out. And for those of you that have dreams of stardom, you or if you want to make it into a Netflix documentary, you may show up in the mysterious disappearance section. But personally, that's not how I want to be remembered. So this presents a unique opportunity to testing out high volume sampling. The kit is similar to soil vapor extraction pilot testing, starting with the extraction point, which is a 2 to 3 inch PVC pipe, drilled and inserted and sealed in the foundation that extends below the slab. You have a lung box, which pulls in air to be measured by, say, a HAPsite to get that real-time analysis, vacuum gauge to measure pressure and suction, a sampling port connected to a sumer canister to collect samples for lab analysis. You'd have an anemometer to measure airflow or air rate, flow rate, and a blower to create a vacuum. But a shop vac works just fine and is cheaper to buy than a conventional blower that you have to rent and ship to the site. Then this blower is connected to a clear plastic mylar tube, which is may not be able to see it so well, but there's a clear plastic tube resting right below the text that says exhaust to outdoor air. And this just directs the extracted air to outside. Considering the low emissions of VOCs on a ton per day basis, a permit is not usually required for discharging to the outside air. But if you do experience any sort of say issues with discharging to outside air, you can always attach a carbon filter to address the VOC emissions. And at a spacing of about 15 to 20 feet from the installed pilot hole, you can install vapor pins to measure pressure changes to assess radius of influence. All this can be done within a matter of a couple of hours as far as installing it and getting the system operational. So getting back to the example, with HVS, they were able to limit the number of soil vapor mitigation systems for as opposed to having to do a complete remedy for the whole 20-acre footprint. They only had a focus on a 1-acre area that could be effectively addressed with a soil vapor mitigation system with a significant cost savings of in excess of about $5 million. So what you're seeing here, the green circles were the radius of influence that was observed for each of the HVS locations. In the northern and southern quadrants, they didn't detect much VOCs, hence the larger spacing. And these findings concentrated investigation in the middle, where VOCs were measured. And what you see in that black outline is where VOCs were most notable and was observed an opportunity for mitigation. So here we see in pink is the revised conceptual site model for the targeted area for TCE and installing a soil gas mitigation system. What was observed with the clean water lenses here, you can see below the helicopter, helped mitigate VOC migration to other sections of the building. And although the field team was not allowed to enter the Black Hawk helicopter maintenance area, they were able to capture the soil vapor beneath these restricted areas, like taking a straw and sucking the air out right below it, and found no indications of VOCs. So we were able to implement a remedy without being terribly disruptive, as this whole study was conducted over the course of 2 weekends without interfering with normal day-to-day operation during the work week. All right, we made it. Now we're going to wrap up some of the findings from this this lecture. We covered a lot of ground here with tools for temporal variability, preferential pathways, and spatial variability. Within temporal variability basket, we learned about the continuous real-time monitoring with GCECD that are able to collect and analyze air samples from several different building zones, which can inform the user of where VI exposure may exist and inform the user of multiple cause and effects relationships. So say at night when the bay doors are closed, you may see a rise in TCE, but during normal operation when the bay doors are open, TCE concentrations are well below action levels. So, however, there are several caveats associated with the technology, even though you may be able to assess this cause and effect relationship. There are some aspects that may not be so attractive, such as the high potential costs, the need for dedicated space, and sensitivity issues between indoor air and subslab co-locations that may require 2 of these units. For building pressure cycling, we learned you can turn on VI conditions by manipulating the building pressure using the existing HVAC system or blower doors. That is imperative to use pressure ranges that are within normal operating conditions. So it can be a challenge to use consistent pressure changes within a large or old industrial building. To assess preferential pathways, we discussed tracers, surrogates, and indicators that can be used to assess VI migration. And that Radon is an excellent surrogate for identifying possible VI exposure, but requires low exchange rates, air exchange rates, and measurable radon concentrations beneath the subslab. And that VI conditions are more prevalent during negative pressure settings, which is evident during, say, heating scenarios that can occur over the winter season. And lastly, assessing spatial variability using high volume sampling, which enables coverage of a large superficial area in a relatively short period of time and accessing restricted areas, so you don't create problems with not knowing what risk may lie in an area that's inaccessible. Though you need to be cognizant of the subsurface permeability and how you'll manage extracted air, so you don't run into a situation where you're subjecting your field team to TCE being discharged inside. And that's really all I have. As far as the references I had mentioned, on the second bullet here, you see the next website that has links to numerous fact sheets and many of the ones that I had discussed in this lecture. And I hand it over to Amy to field any sort of questions.
Thank you, Travis. We have been collecting the questions that were submitted through the Ask a Question box as the presentation was going on. I'd like to invite you to submit any additional questions now, but we need to jump right in to cover these questions that we've already received. The first one, Travis, is, can the GC-ECD measure multiple compounds from each of the different locations? For example, they measure PCE, TCE, and BTEX compounds simultaneously?
Yeah, they can measure compounds from multiple units simultaneously. Just as I mentioned earlier, the thing to keep in mind is the runtime. So you're looking at a runtime about 10 minutes per compound per sampling unit. So if you're looking to assess multiple compounds and in multiple sampling units, you just got to be cognizant of the time that it takes for these machines to measure each one. So this, as a ballpark range, I would assume about 10 minutes per compound per building unit.
All right, thank you. The next question that I'm going to give to you is, how was the radius of influence established and confirmed for the high volume sampling?
Yeah, so they would install, say, vapor pins or sampling ports with a drill and with some tubing connected to a manometer. You get a indication of pressure fluctuations. And so as they're pulling from the PVC pipe that is connected to HVAC system that's pulling in air, you're getting pressure reduction readings from these, you could call it monitoring points, where you're just seeing reductions in pressure. And so as you're sucking from the main unit, you're seeing pressure fluctuations from these monitoring stations, and then that can give you an indication of how wide is this radius of influence for these high volume samplers.
All right.
Similar sort of applications used in groundwater. So if we have our extraction well, and then you can think of it as these Century well, they're just detecting fluctuations in groundwater depth. So it's a similar application for high volume sampling.
And I have another question about the high volume sampling. You briefly mentioned how HVS can be used to measure slab leakiness. Can you elaborate on that?
Yeah, so as you're pulling in air from the subslab, and you have these monitoring points around the perimeter. As you're pulling in air, you'll see whether you're getting much in the way of suction. So if you're not getting much in the way of suction, it'll cause fluctuations in the reading, as well as you can have manometers that are maybe near the surface, and you can just detect any sort of air exchange fluctuations near the surface. So if you're seeing like if your vacuum is just not really pulling in air, but you know it has high permeability in the subsurface, that could be indication that there's something weird going on with indoor air, and it may makes for a need for additional investigation. But you can use tracers as well. If you inject a tracer in the indoor air and you're seeing that reading in the subsurface as an indication that there's some leakage. So there are different applications, say, to assess leakiness in addition to using the HVS system. You can it's just like an additional line of evidence, I would say.
All right, thank you. The next question that I'd like to give to you says, thanks for your talk with very useful information. In the study, you presented that you took a building-centric approach. In developing remediation systems, it is necessary to incorporate the external factors such as climate, wind, ground cover, etc. Can you share some of your thoughts on this issue? Would you like me to read it again?
If I understand the question, it's
okay.
Yeah, if you could read the question again.
Yeah. Okay, so in the study you presented a building-centric approach. In developing remediation systems, it is necessary to incorporate the external factors such as climate, wind, and ground cover. What are your thoughts on this?
Yeah, so with respect to external factors, the one that really comes to mind, I would say, is background concentrations. So it's important to, well, in the NESDI 554 study, we would take background concentrations for BTEX compounds and VOCs to get an assessment of what is the ambient air concentrations that were observed, and to see if this would have any influence on indoor air concentrations. So as far as external to the building footprint, it would be recommended that you get an assessment of what is outdoor ambient concentrations that may confound your indoor air results. That's why doing background studies or background assessments is sort of critical before you make any determinations whether you have a VI exposure risk. You want to ensure that you have a proper understanding of outdoor air concentrations.
All right, and I think we have time for one last question. What are your thoughts about using 1,1-DFA as a tracer compound?
I'm not familiar with that tracer compound, but if it's not commonly found in indoor air products, I would think it makes for an excellent tracer compound. The thing is, it has to be measurable in the subsurface as well at concentrations, say, above 5 ppb. That would just enable you to ensure that you're getting adequate indoor air concentrations. Because one thing to take into effect is attenuation factors. So if you have, say, a high concentration, if you have a really low concentration in the subsurface, the subslab is just going to mitigate the ability for you to read it in the indoor air, even if you have like leaky surfaces. So one thing to just bear in mind that you have measurable concentrations in the subsurface that would be sufficiently high enough to get any sort of measurement in the indoor air, and that it's not a compound, which it doesn't sound like it is, that's commonly found in indoor air products. So my main caveat would just be that you have ensure that you have high enough concentrations and coverage in the subsurface to use as a surrogate.
All right. Thanks to all of you who submitted questions, and Travis, thank you for your thoughtful answers. I'm sure I speak for many of our participants when I say that I gained new information about how to use several technologies to better understand the sites where they're being applied. I want to be sure that all of you are aware now of the contact information for our NAVFAC points of contact for vapor intrusion. Not only Travis, but also at NAVFAC LANT, Teresi Walker is available to support these types of sites and projects. So with that, Travis, if you'll move on to the last slide. As we wrap up, please use the survey links that you'll see currently displayed in the chat box in the announcement box to take our short 3-question survey. The survey should take less than 2 minutes to complete, but it provides us with valuable feedback. Please note that I've provided different links for those of you who are on NMCI network and those who are not. This should make it easier for you to access and respond to the survey questions. Our upcoming webinar topics include environmental sequence stratigraphy, so keep an eye on the T2 email for that announcement. If you're not receiving our T2 email already, you can put a message in the chat box or in the Ask a Question box to be added to the list. Thank you all again for attending the OER2 webinar, and we look forward to having you back next time. All right, we are clear.